Good morning, mathematicians. How's everyone doing? There's a very special guest standing in the corner who might say hi or might not. I don't know. But he's the reason why I have to mute a certain group chat before I go live usually. So we'll see. Not. I don't know. How many subs till he's the reason why I have to mute best friend list revealed. Oh, I didn't mean to go to open editing this video while live. I'll show you guys some code and stuff in a second. I was screwing around with some code yesterday instead of doing things I was supposed to be doing. As one does, you know. As one does. Oh, damn. I'm frozen. I didn't even know that could do that. I don't even know if I'm streaming right now because we're frozen in time, but not in space.
Whoa.
Yeah. Oh, okay. We're still working here. Yeah, people in chat, you gotta let me know if you're here. So basically, yesterday I was talking about, I guess maybe to get you guys caught up, I should bring up my notepad. I was talking about my undergrad research that I did, and we were talking about these polynomials that track the connected induced subgraphs. Well, and I was sort of pontificating about the distribution of the numbers of connected induced subgraphs. And so I wrote some code here to plot the distributions. So, for instance, this, if the code does work, what do you mean graph poly isn't defined? Oh, it's taken a minute to initialize. Probably because I'm enumerating over the list of all graphs of order up to 9. So, gotta be patient.
And it's the distribution of what number that you're going to show?
The number of subgraphs. So for each graph, I'm tracking the number of subgraphs, which are connected.
Okay.
So every vertex you can get to the other in a path. It won't be like two disjoint pieces.
Sure. Okay.
And it's induced, meaning that if you have two vertices, if two vertices exist in the subgraph, and if they have an edge between them in the parent graph,
okay,
you must force that edge between them in the subgraph.
Okay.
So, like, for example, if I took the cycle, then this would not be an induced subgraph,
Gotcha.
right? But this would be an induced subgraph.
Yeah. Okay.
Arad, you think you finally found a good way to think about classical Satake isomorphism, and maybe even a conceptual motivation to get perverse sheaves into the mix. Interesting. Now it just remains to write some actual proofs. You should send me some of those actual proofs, because I'm very interested in that. I mean, I definitely have a couple different ways of thinking about the classical Satake isomorphism. Yeah, I think there are good ways for that, but I don't know about the geometric Satake isomorphism so much, or motivation for why perverse sheaves should get in the mix. So please do share that when you reach some conclusions there. Okay, so for example, right, if I run this, So this is the plot. These are the plots for all of the graphs, all connected graphs of order 3. This is the plot of their polynomials. So the x-axis is the order. So of course, I only defined it for the discrete integer values, but the x-axis is the order of each of these graphs. And the y-axis is the number of such graphs that exist. And so it's interesting, actually, so here I'm just looking at some random graphs of order, I guess if I do this. So here's some random graphs of order 7, right? So you'll notice as I just go through the list and generate, a lot of them tend to look like this, where they just have this distribution that just sort of monotonically increases, and then somewhere around the middle it hits a peak, and then monotonically decreases. So that's very interesting. So I wonder if I can do like statistics on the distributions that show up, because as you see, like it just all seems to be, and okay, maybe these graphs are all clustered together, right? So let me like jump down to 30. Okay, so this one's different. We do see there's some behavior where there's a double peak behavior, but it's very interesting because this does not seem to be typical behavior. So most of them just seem to have a single peak. And generally, this behavior seems to be general as well, where the second, this dip, seems to always be not too far away from the first peak. So see here, for example, the dip only seems to be by 1. And so, yeah, I just wonder, it makes me wonder if there's some like statistical thing that one can say about this. If one could prove some theorem about the distribution over all graphs or something, it would be really interesting. But this also could just be an artifact of the fact that I have small orders of graphs. Seek, we're talking about, I wrote some code yesterday. I don't remember if you were here yesterday, but I was talking about some of the research I did in my undergrad on connected induced subgraphs of a graph. And I decided, I was just thinking about it, and so I was like, oh, I want to write some code, because I was sort of wondering out loud yesterday about like what the distributions of the subgraphs are. And yeah. Anyways, interesting. Oh yeah, sorry. Just to finish one thought, I was gonna say it's conceivable to me that like, yeah, these graphs are only like, this is graphs of up to order 8 right now, I guess. And so it's conceivable to me that perhaps actually more like if you go to larger graphs, maybe that gives you more space to have more peaks and valleys. So I don't know. I'm kind of, I'm thinking about just like writing down some random, or maybe, so I don't know if, the problem is I think the iterator, like if I want to range over graphs, I think so for G in graphs N, right, this grabs graphs of order N. I think if I do this, I think it tries to like initialize all graphs of order 10, which is sort of a problem, right? Like I would want to just grab random graphs of order 20 and then just like see what pops out. Yeah. What's the application? I have no idea what the application is. I don't care at all. I mean, we spun some bullshit about, there's this hilariously named thing in graph theory called the Wiener index. And anyways, it apparently does have actual applications to chemistry. There's certain things like if you look at you take the graph of the underlying molecular structure and then, compute the Wiener index, it can tell you some sort of like structural properties. But for this index. So we spun some stuff in the paper, for the funding of like, oh yeah, well that was a useful index, so why don't we explore some other useful index? So we said, oh, maybe it's something like that, but yeah, I don't know. The reason we did the research is because we thought it was an interesting, fun, and tractable question. Have I seen any uses for turning algebraic varieties into tropical varieties to solve problems? No, I would say, other than the fact that I'm just vaguely, generally aware of the existence of tropical geometry. No, but I haven't personally. I don't know exactly how it works, but I'd be interested to learn. I'm really interested. There's this thing that's really interesting. So Peterson graph in tropical geometry. It's supposed to be some sort of. So I'm obsessed with the Peterson graph, as you know. It's an example of tropical. Peterson graph also makes appearance in tropical geometry. Yeah, so it has something to do with. I mean, I'm obsessed with the Moore graphs for the Peterson graph and Moore graphs for a whole bunch of reasons. But this line always caught my eye. So the cone over the Peterson graph is naturally identified with the moduli space of 5-pointed rational tropical curves. I don't understand the statement at all. It sounds so cool. I would love to, especially because it's just like, yeah, more interesting things about the Peterson graph. Like, yes, please. Yes, please. Is the issue here the efficiency of Python or the actual asymptotic issue with iterating through graphs? I'm guessing it's the asymptotic issue of iterating through graphs, right? Because I don't. I also don't know how the graph. I mean, it could also be the way of how the graph constructor is implemented. But how many graphs are there on 10 vertices, let's say? Each of which have even degree. Nah, that's too restrictive. Okay, gosh. Wow. So, but yeah, here's the thing. Are we getting up? Look, there's 2 to the 36 labeled graphs on okay, sorry. That's labeled graphs on that doesn't that's not cutting down up to isomorphism. So, what cone? Yeah, that's a good question, New Wave Infantry. I don't know. I don't even know what cone they're talking about exactly. I mean, I suppose that there's let's see, what did it say? What was the exact wording again? The cone over the Peterson graph. I'm guessing that there's some analog, right? There's some we can right, the cone over a space. There's some way. What is it? You take something this is just a guess, but right. So a cone is like this. So you can imagine that you've taken a disc, right, and then you take the product. You take the product of the disk with the unit interval, right? Cartesian product. And then you quotient out so that this all gets squished together, right? So you quotient out by this equivalence relation, which relates all the points. So D, all points where the second coordinate where D and E range over all points, right? And so then that collapses this to a cone. So you could do the same thing for a general space, right? You could do something like this. And my guess is that you form some analog of this. And so your space X you take to be the Peterson graph. But again, this is all happening in some sort of tropical geometry context. But this is a guess. I don't know. Do not take my word as given. Go fact check me. The app I'm using here is CoCalc. So what it's doing is it's running Sage ultimately, which is, yeah. is just awesome. I don't know. Math Lab and Mathematica, I've never really enjoyed that much. Sage just has so much incredible functionality. There's just wild stuff that like I still find surprising you can do. Like you can do like integration on manifolds and things like this in Sage. So I think it's just fantastic, and it's open source. And there's like they have their own separate community, like a Stack Exchange. Where I found it extremely helpful when I was using Sage Code for my master's thesis research. Everything becomes piecewise linear in the tropical world. Yeah, I'm vaguely aware of this being true, but yeah, again, I've never studied it properly. Maybe it's more analogous to the cone of a projective variety in algebraic geometry. Oh, that's probably true, actually. That's probably true. Cone of a variety. A cone is a generalization of a vector bundle, specifically given a scheme X. Oh, rel spec. Okay. Is a quasi-coherent graded OX algebra called the cone or affine cone of R. Similarly, relative proj. Aha. Projective cone. Interesting. Does it generalize as vector bundles? All vector bundles are this? That's a cone in homotopy topology. Yeah. The term cone might mean something else. The Collar cone of M is a set of all classes of Collar forms? Oh. Well, I don't know about that. But maybe you're right. Maybe that's related to this as well. I have absolutely no idea, I'll be honest. I do not have a CoCalc subscription. As you can see, the yelling went away. Sometimes it yells at me about the fact I don't have a subscription. I'm not paying for that. I did pay a little bit for it once because I wanted to do some I needed more computation power to I had some other side projects I was screwing around with. It's a graph. Wouldn't it be a cone in the categorical sense? Well, maybe. I mean, maybe, but I'm guessing because we're in the world of tropical geometry, probably what I'm guessing, I guess, what makes the most sense to me, and again, I have no idea. I'm completely guessing. So someone go find a textbook and correct me, but I'm guessing that it's a cone in the algebraic, or rather, I mean, tropical geometry is whatever, the piecewise linear approximation to algebraic geometry. So I'm guessing what we would do is take, stare at this construction, then define some sort of analog of that, some sort of thing that should be the analog of this in the piecewise linear world. Yeah, I don't care, Boris. I am crazy. I'm going to slander Mathematica all day. I'm going to start a turf war. Me and the homies are going to roll up with our Sage code printed. We'll 3D, print our GATs with Sage code. And it's definitely not that cone. It's just an example. Oh, I see. Yeah. Alternate use of the word. But then again, compact Collar manifolds of Hodge type correspond to projective varieties via Gaga. Yeah, so I don't know. That's the blessing and the curse of math, you just can't know everything. There's just too much. And I'd love to, I don't know, 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 I'd love to You know, if I were still in the course taking component of my life, and I happened to be at an institution that offered a course in tropical geometry, you bet your butt I'd be doing some tropical geometry. Yeah, but I don't know. We might. I think we're gonna. Mathematics is good. Mathematica is good for special functions. Oh, okay. I'll take your word for it. While I happily stay in the bliss of computing with Sage. I mean, I don't know. Maybe these other things have. Here's the other big one. Sage is also like connected to LMFDB, so there's stuff like you can go to LMFDB and then you can click on a thing and it will like open up a link to Sage code for you, and vice versa. You can like compute. I don't know. You can like find a group in Sage and then you can like ask it, oh, like what's the, find a Galois group, find a field extension with this Galois group or something, and it'll bring you over to Sage. So there's like a lot of compatibility and functionality between Sage and LMFDB. So that's another big one. Mathematica doesn't have that. So yeah, I think I'm right about everything, especially Sage superiority. You sure there's some cellular automata GAT you can make on Mathematica? Okay, well, I'll have to consider that. You don't even like Sage? Parsley better than Sage? Yeah, I don't know. I don't think I really use either of those in my cooking. And then thyme better than Sage, yeah. Is the ordering is the superiority ordering on herbs totally ordered? Is a complete order or not? Heisenberg groups? You're just asking what a Heisenberg group is? Or to define something like a coherent sheaf on a tropical variety, you would need to define modules over a sheaf of semi-rings instead of rings. Okay. And you can't find anything about that. Well, then, are you sure that that's the right approach to take? Like, I mean, I agree. That seems like a sensible thing. But again, I don't know. I know absolutely nothing about tropical geometry. So, according to Grok, well, let's also take that with a grain of salt. Tropical varieties show up in mirror symmetry. Actually, I do think that's true, but it's above your pay grade. My pay grade as well. Yeah, what is the Heisenberg group? The Heisenberg group is basically, it's like upper triangular matrices. It's like what, one? I think it's just. Is it just this? Is just the upper triangular matrices in GL3, the classical Heisenberg group. It's an example of a nilpotent group. Yeah, I was right. Haha. I am a genius because I remembered this basic thing. But the Heisenberg group is actually very, very interesting. Both it sort of does the existence of dank Kush suggest the existence of dankest Kush? Does the set of all Kush have the least upper bound property? I don't know. That seems like a non-trivial theorem to establish. You don't know about herbs, but isomorphism classes of fields of a certain characteristic should probably be totally ordered, right? Assuming global choice. No, I don't think that's true. I don't think that's true. No, I don't think that's true at all. Definitely not. Definitely not true. That moment when extra special P groups. Is that what the Heisenberg group is? Yeah, so originally it comes out of physics. Like, I think the Lie algebra of the Heisenberg group corresponds to like the momentum. Yeah, the momentum and the like you can encode basically the uncertainty principle, right, through the non-commutativity of the momentum and position operators, and that's kind of manifest here in the Lie algebra of the Heisenberg group. There's originally like reasons to study it for like these reasons, and of course there's generalizations. But also, what's really interesting is I sat in on this course on what's called the Weil representation. So this is a way of constructing certain like representations in like the business of like Langland's automorphic form stuff, and so that's what we see here through the Stone von Neumann theorem. There's this the unitary. There's some sort of way by passing through the Heisenberg group where you construct these special representations of what's called a metaplectic group. And in fact, you can then push this down. And actually, speaking of my master's thesis, there's some way, again, I don't understand it all that well, but there's some way that, for example, here you can relate this to representations of the unitary group UPQ. Yes, Yamin, exactly. The theta correspondence. This all bakes into the theta correspondence somehow. Again, my understanding of the exact process is kind of nebulous, but yeah. Connection with the Weil algebra. So there we go. And then there's D modules. So everything comes full circle. Yeah. So the Heisenberg group, in short, very, 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 very interesting thing. I would also be something. I have this book called. There's something called the orbit method, where it's very much in line with my research, and I think probably inspired some of Vogan's takes on the p-adic case, where basically you look at certain nilpotent orbits of some group action, and you should be able to connect this to representation theory of like certain unitary representations, and then like use the geometry to make these certain kinds of computations. So yeah, so much math is there in quantum physics. Physics students have to learn a lot. I mean, yes and no, right? There's I mean, the more you know, the better, I guess. But then, it's also like, there's you do what you can with the tools you have, I guess. Q adjoins square root 2 does not embed into Q adjoins square root 3 or vice versa. Exactly. Yeah, definitely not a total ordering. Yeah, not everything is comparable. Hello, you've been hearing the word super before. Common terminology. Is there a connotation for it? Wait, sorry, what? Well, generally super, it's kind of stupid. Yeah, exactly. As Bohr said, basically just means Z2 graded. It's also funny you bring that up because that's also in my thesis is super vector bundles, which makes it sound so exciting, like it's a fantastic thing. And it's just literally a Z2 graded vector bundle. That's all there is to it. Anticlimactic. Okay, I think that's going to do it for office hours today. So thanks everyone for joining me, and go prove some things about I don't know, the Weil representation, and tell me tomorrow what you proved. Okay, bye.